Yeah, good afternoon everybody. Okay, so today I will present IO buffer, latchup, ESD and layout. First I will tell IO buffer. So why IO buffer is required? So there are a lot of points. First, if we want to drive different kind of load, then we need proper IO buffer. Then to get the clean signal from incoming noisy signal, and to provide proper interface between different ICs with different signal level, and isolate internal circuit from external effects, and translate incoming or outgoing signal level to the required internal external signal levels. Okay, so I think it will better if I explain in the page. This is IC integrated circuit. Then this has some pins, input output pins. Okay, so let's see, this is one pin, this is another pin. Okay. Now this is one IC. So this is another one. Now consider this is output of this is IC1, this is IC2, and this is IC3. This is the PCB. Okay. Now this is the one system, and here this is the output of this IC1. This is going to the input of this one IC2, and this is also output of this one connected to the input of this one, and this is the input type, right? This is the output input type, and this is output type. This is output type. This is driving this chip, and this is also driving this chip, IC3. Okay. Now here, some consider here we have some different IC or some different routing, something like this. Here some PCB trace. Here also some PCB trace. Okay. Now, so this is the required signal, right? If you see the signal here, consider just we consider the clock signal here. This is the clock one, and this is the data one. Okay, so ideally clock will be something clean clock. This is the clean one, right? But here, due to this interference, it will be so this is very bad signal. Okay, so this signal is here. So consider this labeling. I am labeling this A. So A is here, and so we have to clean, we have to rectify, means we have to get the clean signal from this noisy signal, right? So we'll do that one by using IO buffer here. Okay, because consider here this signal, right? If the noise level is very high, on that time it will be something like this. So if we want to drive one flip flop using this clock, that flip flop will not be drive properly, right? So you have to get the clean signal from this signal. So how to get that one? And we'll get the clean signal using the input buffer, because this is the input of this IC. So we will call this buffer is the input buffer, input type buffer. Same thing here. Consider this is the PCB trace, right? So consider it has some huge load here. Consider some capacitance here. Or here some capacitance. So this pin should drive this huge capacitance, right? And the circuit, internal circuit here should have sufficient capacity to drive this load. Otherwise, consider here without the capacitor. Consider this is the signal without capacitor. This is without cap. Okay. And if there is no proper buffer here or driver here, then the signal will be something like this. So it will very bad, right? So to drive that load, we need proper driver. So that is also called driver or output buffer, we can call it. Okay. Now this is the one type, input type, output type, right? Third one is the bidirectional thing, right? Here actually the if you see the signal flow is one directional. In some place consider we have another IC here. We call IC4, and this is communicating with this IC4, and that this is called this is actually input output type. This is the bidirectional type. This is we can call it, okay, we can call it IO type, input and output both, right? So it is driving this IC4 and also same time receiving signal from the IC4. Right. So I have divided that one here. So depending on the direction of the signal flow, we can call buffer is three type: input, output, and bidirectional. Right. So this is in the top level. Okay, I will tell details. Now there are also different type of signal level, right? So here I have told very simple way, right? Here we are considering every IC has the same supply voltage. Consider 2 volt or 3 volt, something like that. Every IC has the same supply voltage, right? Now consider IC1 has 3 volt supply, IC2 has 5 volt supply, and IC3 has called 7 volt supply. So we have to interface properly, right? Now otherwise, okay, we can face a lot of problem. No, okay, just I am explaining that one. Now consider the circuit here, this VDD for IC2 consider 5 volt, right? 5 volt, and VDD IC3 consider 7 volt. Now I first consider simple push-pull kind of buffer, right? Here I mentioned level shifter, Smith trigger, then unity gain buffer, push-pull buffer. First I will tell the simple push-pull kind of buffer, right? This is a simple push-pull. This is the PMOS, this is NMOS. Consider. Okay. Now this is 5 volt, right? This is in part IC2. Now consider this is bidirectional pin, right? So we can consider here one pin is here, and the signal level this is consider IC3, and here. Okay. So this is the output type, right? Now we have to draw the input type. Consider this is the input buffer, and this is connected here. Okay, this is bidirectional thing, right? And here, so when we are driving the IC3, on that time this portion will be off, right? So some signal will be there to turn off this part. This is the input type, right? And we have to turn on this one. It is driving the signal, and when it is receiving, this part will be off, and it is only receiving this signal through this path. Now this IC3 has 7 volt supply. That means signal level here 0 volt, and this is your 7 volt. Okay, so during that time when it is receiving the signal, right? So when signal is coming in this direction, on that time this is off, right? So if we want to turn off PMOS, how do we have to do? We have to give 5 volt here, we have to give 0 volt here, right? Now bulk of this transistor is generally connected to high potential, that is 5 volt, and for this one is connected to ground. Now if we consider the 0 volt signal here, first consider 0 volt has come here, this is the 0 volt, right? This is 0 volt come here. So how do you have around that time? It is fine, no problem, it will receive signal properly, no problem, right? This is off, right? Now consider it has gone to 7 volt. So now we have 7 volt here, right? Now you think NMOS is already off, right? This is 0 volt means this is off. But if you consider the PMOS, consider this is drain node, right? So this is 7 volt, this is 5 volt. So gate is lesser than this one, right? That means PMOS is turned on. So current will flow through this way. Right? But we don't want that one. That means on that time there will current flow through this path. This is very bad. So that means we need something here. That means when it is receiving 7 volt, because it has 5 volt supply, it has 7 volt supply. So signal level for the IC3 is 7 volt, right? Maximum 7 volt. So we have to turn off. So this is on the time PMOS will be turned on. And second thing, if you consider here, if I draw the PMOS, this is PMOS, this is bulk, right? PMOS means this is P plus, this is P plus, right? So we have diode something like this, and one diode something like this, right? So now here you consider this is your N type, this is connected to here source, this is 5 volt, and this point is 7 volt. Now consider this diode also will be turned on, right? So there are two paths. One is through channel due to the turning on of the MOS, and second one through the drain bulk diode, junction diode, right? So we need proper buffer circuit at the IC2 level. So that is actually I will call that is okay. I missed that point. That is the 5 tolerance circuit, some high voltage tolerance circuit that will be there. Okay. So same thing can happen in the input side also. Consider IC2 has 5 volt, and here this is 7 volt, right? So one thing, if we see this is the 0 volt, right? And consider this is your 5 volt, right, for IC2, and we are using consider 0.5 micron technology. So the maximum voltage for 0.5 micrometer technology will be something 5 volt, right? So on that time, if we put more than 5.5 or 5 point consider 6 something like that, on that time this oxide here, this is 0 volt and this is your consider in this case 7 volt, right? So on the time this oxide will be traced. So some circuit will be there to avoid that trace. Function, there will be no wrong functionality, right? But the longevity of the transistor will reduce. So we have to add some extra protection here at this point, right? So actually to avoid the trace of the NMOS transistor, you have to put some circuit at this point, and also to avoid the current flow here, you have to add some protection circuit. So that is the tolerance circuit, right? This is the output side. If we consider the input side also, so input side, is it clear? Now consider input side, right? Now first consider simple inverter. Simple receiver is the inverter, right? We can use inverter as receiver, right? Now consider this is your 5 volt, and this is considered IC2. Now consider IC1 here. So for that consider it as 3 volt supply, right? So signal level will be here 0 to 3 volt. When 0 is coming here, right, this is connected here. When 0 is here, there will be no problem, right? This is off, this is on, so we will get high 5 volt, right? Sorry, this portion will get high 5 volt, right? Now if this signal is here at this point, so this is considered A point. During A we are getting here A, right? And now we consider this is the B, 3 volt. So 3 volt has come here. On the time if you see, on the time what we actually NMOS should be on the time, right? But on the time you see this is also on, so it will act as divider, right? Because PMOS is not turning off completely, so you have to turn off that one. So some circuit we have to put at the input stage. So here some circuit we have to put here. That is called tolerance circuit. Okay. So this kind of circuit will come when we will handle different type of signal level between different ICs. Now this is the on the PCB level, right? This is on this level. Now if we see inside IC, consider our design one is the IC2. We are planning to implement IC2, right? Now here we consider this is the 5 volt supply, so we are using 0.5 micrometer technology. Now if you see actually for if we want to get more speed, we have to reduce the lower technology, right. So in recent process you can find we can use two type of MOSFETs. One is considered 0.5 volt, we can 0.5 micrometer MOS we can use, we can use 0.35 micrometer also we can use. So at the time we can use two, right. So to get the speed we are planning to use lower lower gate length for the core transistor. So consider this is the core transistor, this is the core portion, the main processing portion, right. So speed is actually is mainly determined by this portion, right. So we want to process everything very fast, so we are planning to use lower technology, consider 0.35 micrometer technology. So for 0.35 micrometer technology, what we can use? We can use here maximum 3.5 volt. We can't go more than 3.5 or 3.6 or more than 4 volt, because if we use the more than 4 volt, that oxide will be traced, right. Whatever I told here, sorry, here oxide will be traced, right. Electric field will be more, so reliability will be less. So that means we can use here maximum 3.5 or 4 volt, right. But here we need 5 volt. Okay. Now we have to down convert it here, right. This is 5 volt signal, this is 3.5 volt signal. So some level shifter will be there at the input side, right. And here also we need some level shifter, because here we need 5 volts. This is 5 volt signaling, this is 5 volt signaling, and this is 3.5 volt signaling. So we need here level shifter. This is the input side, level shifter at the input side, this is level shifter at the output side. Okay. So as just I am drawing level shifter at the output side. Okay. So we are planning to convert 3 volt signaling to 5 volt signaling. This is the standard circuit. This is the level shifter circuit. This is very standard one. Is it required to explain this one? We now consider we have here 0 has come. 0 means here 0, right? This is off. This is high. This is on, right? So this node will be pulled down, and then this will be on. So this node will be high, and this node will be low. This is off, right? Pull down to this node will be low. This node will be high. And low means this is 0 volt. Low means this is 0 volt, and high means this is 5 volt, right? You try to analyze, you will get this is very simple one, right? This is a simple cost couple one, then this is pulling down node, these two. So this is the this is 3 volt to 5 volt shift at output. Now if you want to shift 5 volt to 3 volt at input side, right? You can use simply an inverter, no problem, right? This is 3 volt, and here signal is 0 to 5 volt. We can use it, no problem, right? But we have to use the proper size of the transistor. Here also we have to properly size the transistor. These two should be strong, otherwise this transistor will not be able to pull down this node, right? Because this is the bistable thing you can consider. So this stage will try to hold the state, and when high will come, this transistor will pull down that node. Okay, so this transistor should be strong. So that means we have to do the sizing. That's all. And for this one, we can consider this is 0 to 5 and this is 0 to 3, right? This simple inverter we can use, right? There will be no problem, right? When 5 volt will be there, this is off. When 0 will be there, this is off. So one transistor will be on at a time. So this is your 5 volt to 3 volt shift.
in the 5 volt to 3 volt shift, so in general, if we consider a higher voltage to lower voltage shift like this, then isn't that the limitation of a particular technology coming into the picture? Like for 0.18 micron, we have a limit of 1.8 volts, so we can't actually apply more than that.
No, actually, in particular process, there are actually different kind of transistor. So you can use 0.18 micron, you can use 0.25. So at a time you can use two. Okay. So also 35 is 0.35 micron is also there. So you can use 0.18 or 0.18 and 0.35, or you can use 0.25 and 0.35. At a time you can use two. Okay. Now the unity gain buffer. So here we are considering a digital signal 0 and 0 and VDD, right? But if we want to receive or transmit some RAM sort of thing or some analog signal, so we need some buffer, right, to isolate the internal circuit from the external world. So for that, it is preferred to use the unity gain buffer. That means simple op amp we can use here. Right. But when we are using the op amp, we have to choose proper op amp, right? Because here you can see this signal level is considered 0 to 5 volt, right? This is analog RAM signal, right? So that means this is also following the same signal, this node. That means we can see that the common mode level is 0 to 5 volt, right? The supply of this is 5 volt and this is 0 volt. That means op amp should be op amp should have rail to rail common mode level. So for that we have to use both N pair, P pair, P differential pair. Then you have to combine both. Okay, those things will come. This is a simple unit gain buffer to receive or to transmit analog signal. Now, if you consider the high speed signal, you consider some gigahertz signal you want to transmit, right? Now, consider you have VCO. Consider this is your IC2, and we have some VCO here, okay. And here this is the IC3. We want to transmit that signal. Consider some 5 gigahertz signal. We can't connect directly VC output at pin, because pin has particular capacitance, resistance, right, inductance that will affect the VCO. That means VCO inductance, or if you use the LC VCO, then VCO inductance capacitance will change. So the operating frequency will change, and we need some isolation. That means we need some buffer, isolation buffer. So on that time, so high frequency, so this circuit will not work for high frequency. We have to use some different kind of circuit. So it is preferred to use source follower thing. The resistive load source follower. This is NMOS thing. So this is the output, and this is your input, right? So this kind of structure we can use for high frequency. Okay. Now I already covered level shifters, tolerant, then unity gain buffer, Smith trigger. Okay. Actually, for low frequency operation and also to remove the noise, we generally use two threshold voltage, right? I think consider this is the ideal signal. If we have some noise, something like this, right? So we can use two threshold voltage, right, for the low frequency operation. So one, actually when it will come here, it will switch. When it will go down, it will switch here. So two threshold, VT1, VT2. I think you have already read that Smith trigger cycle, right? So that cycle also we can use as buffer. For actually for low frequency operation we can use, very low frequency operation, kilohertz level, something like that. Okay. Okay, now I'll do the latch up thing. So up to this point, is it clear or not?
So we can use the Smith trigger as a buffer only in digital circuit, or we can also use an analog?
No, digital. So what is latch up? This is actually very common problem in a CMOS process. Okay, so actually this problem, latch up problem, generally comes in the here. If you see here, this is the core region, and this is, we can consider this is the IO region, right? This side is called IO region, this portion, because all IO buffer generally sits here, okay, near to the pin, and this is the core region, main processing portion, right? And when it is driving capacitance, that means it is driving huge current, right? That means the switching phenomena, means current, sinking of current and sourcing of current, huge amount of current is happening in this region, right? So actually generally latch up occurs in the IO side mainly. Okay, so and latch up is very common for the CMOS process, because I will tell why it is very common for the CMOS process. And when the external transients above supply or below the ground signal, that also helps to cause the latch up. Okay, okay, I will tell the circuit, then it will be better. Okay, this is the cross section of one is the NMOS, this is the NMOS, and this is the PMOS, right? Now consider simple inverter. We consider a simple push pull IO buffer, push pull output buffer. So inverter you can consider, right? So here this is the NMOS, this is your source, this is drain, right? This is bulk, and this is also drain, source bulk. And for PMOS, that will be source and bulk connected together, connected to VDD, and here is connected to ground, right? Now latch up occurs due to this lateral bipolar transistor. Now if you consider this is this source, then this substrate, and this NOL forming NPN transistor, right? It is shown here, and here also same way, drain or source, and then your this is your substrate for the PMOS, and then this is the common substrate. It's forming the PNP bipolar. So they are connected something like this, right? So this structure is clear. This is the lateral BJT. These things. If we simplify this one, only the BJT portion, we can see something like this. Just to follow this one, right? So this is resistance. This is the substrate resistance. Substrate resistance for the NMOS. This is the substrate resistance for the PMOS. You see, connected to this is your base, right? Base of the NPN, right? And this is this node DN1. We are not connecting this one, okay? Because when it is inverter, then this DN and DP will be connected together, right? Output will be connected together. Then we can sort it, this and this, and here this is in PNP transistor here. Okay, so the structure is clear. This portion, how latch up happening, I will tell. Okay, so if you go to the next slide here, now consider the signal level here. This is the drain of the PMOS, goes more than VDD, right? Some spike has come here. That means here some spike has come. Now if you see that this junction, this is your N and this is P. So some N junction. So this is the direction of the electric field, right? Now due to this spike, that means this junction, this P plus and this N, is this junction diode is coming forward bias, right? And then some holes are injecting here. So that is the minority for this one, NOL. So that holes are injected here. So if holes are here, and then due to this electric field, then they will be repelled this side, right? Because the ground is here, and electric field will help towards movement, right? For the hole. So holes are coming here, and it is collected here. It is going to ground, right? And when it is going, it is passing through the substrate. So if we model is substrate resistance, so it is going to the passing through the substrate resistance, right? So holes are collected here. That means holes are going this way. That means current is flowing this way, right? That means this potential is more than this one, right? Now if you think this potential is more compared to this potential, right? So that is some positive potential. So this junction N and P, this junction also Pn. So this junction is coming forward bias, right? So that means this coming forward bias means more electron will be injected here. So more electrons are injected here, and when those electrons are coming here, due to that electric field, they are repelled to the substrate of the PMOS, right, and then they are going towards VDD and they are collected here. When they are going, that means some current is flowing in this direction, that means this potential is higher than this, right. So if you consider this junction, this potential is lesser than, this potential is lesser than this one, right. That means this junction is forward bias, so more number of holes will be injected. So then those holes are going this way, and then more electrons will be injected here, and those are going this way. So that is some regenerative process, right. Now if you consider this circuit, that means we are getting sufficient drop across here, right. When more number of electron injecting, more number of holes are injecting, that means more current is flowing, that means drop across substrate is R sub and R annual is increasing. That means this junction is forward biasing and this is also forward biasing, right. So both PNP and NPN bipolar transistor is turning on, and so this is the emitter current, right, current passing through this emitter current, right. So if you see the current profile of the BJT, current profile means gain versus current. This is the common base current gain, this is the alpha, this is the common base current gain, and this is the emitter current. You can see something like this, okay. So when your emitter current is increasing here, your current gain is also increasing, right. So when current flow through this, so more number of electron injecting, more number of holes are injecting, then current is injecting, that means current gain of the BJT is also injecting, right. And now if you can you remember the circuit SCR, silicon control rectifier circuit, can you remember? This PN. So some this is, we split it, PNP, sorry, so this is N, P, N, okay. Now this is connected here, this is connected here, same thing, you see this portion, emitter base, collector base and then collector base. So this is actually forming the SCR thing, and if you find the equation for the SCR circuit, you can see when the current summation of the current gain of this one, so alpha P plus alpha N more than 1, some equation is there, some other you have to derive the equation, so some 1 by something, on the time you can see the emitter current will be very high, means that SCR is turned on, right. That, so that means when latchup occurs, when this current gain, summation of the current gain is more than 1, on the time latchup occurs, and if the latchup occurs, it will you can't avoid that one, that is uncontrolled, you can't control it. So only solution to stop the latchup, you have to remove the power supply, okay. So now if you see here how to minimize the latchup problem, so try to use the guarding means, okay, I will tell that one later, just I am briefly telling what is guarding here, okay. Now here what we have, so minority carriers are here and also minority carriers are here, right. So if we try to stop the flowing of the minority carrier this side and that side, then we can avoid the latchup, right. That means if we put some ring, means we to collect the minority carrier, then latchup will be raised, right. So that is the guarding, we have to put guarding surrounding the MOSes. So I will show that thing when I will tell the layout, right. So first thing is the guarding, proper guarding we have to use. Second thing, spacing between the NMOS and PMOS, okay. How that will help? If we put more spacing between these two, that means we are increasing this region, right, and also we are increasing this region, that means we are increasing base region, right. So if we increase the base region, then current gain will be less for the BJTs, right. So that will also help, that means the current gain we are reducing of the BJT, and also if we put spacing and if we put guarding here, then that will also help to collect the minority carriers. Reducing this resistance, substrate resistance and unit resistance, how to do that one? We are planning to do this one, because if we reduce drop across this resistance and across this resistance, then there is less probability of turning on this one, this transistor and this transistor. So how to do that one? Minimize spacing between source and bulk, this resistance. If we actually, you see this resistance is coming here, right? The source and bulk. See here, this is the, this is your this node, right? Source node, and this is the bulk node. So if we put substrate connection closer to source, that will reduce the this resistance and this resistance. Same thing for PMOS also, right? That is the one thing. Second thing, doping density. If we increase the doping density of NOL and P substrate, then automatic resistance will be less. And third one is the more number of contacts. If we use more number of contacts here, then also that will also help to reduce this resistance. Right. Then if we use wider guarding here, then the resistance for the magnetic carrier, that path resistance for the magnetic carrier will be very less. So instead of going this way, magnetic carrier will be connected to VDD or ground, right? That will also help to reduce the latch up. So those are the steps how to reduce the latch up. Okay. So now is it clear, latch up thing? Okay. Now I will tell the ESD. This is the electrostatic discharge. Okay. So what is ESD? What is electrostatic discharge? And this is very common thing for the CMOS process. For bipolar process, you can see the ESD, because for CMOS process, gate oxide will be there, right? And that gate oxide is very thin. So if electric field is high across the gate oxide, then that oxide will break down, right? So you have to protect that one. But for BJT, that is not there. That oxide breakdown, those things are not there. So for CMOS process or for MOS process, that ESD thing is very common, and that is still people are learning the ESD thing. So there is no particular rule that if you use this circuit, there will be no ESD. There is no such thing. Okay. So different circuit, you have to do ESD differently. So still it is learning thing. Okay. So now consider here, just I have written some point. So as you are probably aware that you have to be very careful when handling most circuits to be sure that you are properly grounded, right? So when you are handling some IC, MOS IC, you can see some belt connected here and then that is connected to ground, because that is required for ESD protection. Okay, that circuit, that proper grounding thing, because you do not transfer any static charge, because you body has huge static charge. You don't want to, if you transfer that static charge, then ESD will happen. So almost any form of friction can generate static electricity, and even human body has static electricity, right? ESD can occur when charges stored in the human body or machines are discharged to the chip. On that time the discharge will happen, right? On that time that gate oxide will break. Just I will tell how it is happening. Now consider, for example, we are just transferring static charge of 0.1 microcoulomb. 0.1 microcoulomb, that is very less, right? Now you consider this equation Q equal to C into V. Now for today's CMOS process, if you consider just one MOS, okay, just I am drawing here. Now consider this is the pin, this is the input side, right? This is the input side. Now this is connected to input buffer, right? Input buffer means, if we consider simple input buffer, that is inverter, right? And that is connected to, this is the IC, and is connected to here inverter. And if we touch, this is the pin, if we touch here, that means charge stored in the human body will transfer here. Now consider that charge is very less, 0.1 microcoulomb, but the capacitance here, this capacitance, oxide capacitance, we consider this one 84 femtofarad. For if you consider W is around 10 micron and L is 1 micron for NMOS this process. This is the capacitance of this portion. Okay, sorry, but this NMOS thing, because it's simple one NMOS. So if we calculate the voltage across this oxide, coming almost 1.2 megavolt. Can you imagine that one? And oxide thickness is considered some 42 angstrom, very less. So electric field is coming almost 3 times 3 × 10⁻12 times, right? Volt per centimeter. That is very huge, and that will breaks the gate oxide. Okay, so that means that is actually ESD, the electrostatic discharge phenomena. So we need some protection circuit to prevent that one, right. So here people are still studying quite a bit about the EHD thing. Now, so that is the thing, when we are touching pin or when we are handling IC using machine, on the time also EHD can happen, right. So how to test the circuit? So before selling your IC, people will ask what is the EHD specification you are meeting, how much EHD specification you are meeting, okay. So that means we have to test the IC properly. So that is there are different procedure to test the IC for EHD thing. This is the very there are three common thing. One is the human body model, machine model, and the charge device model. Okay. So this is the device. This is the IC thing. We want to test it. How to test for the human body model? So we touch this capacitor. First, this will connect it here. We touch the capacitor, and this capacitor will be charged. Then we'll connect this one through 1.5 kilo ohm resistance. This is the body resistance, right? Then that charge is discharging to the device under test. So that is a device thing. Okay, so this way people are testing the EHD thing. This is the human body model, this is the machine model.
So what will do the 1 mega ohm resistance?
This is the body resistance. Okay. This is the not sorry. This is body resistance. No, this is the body resistance. Body equivalent resistance 1.5k. And I don't know. In the standard book they mention the 1.1 mega ohm. This is the standard thing, very standard thing. Same thing you see 1 mega ohm thing. Okay. This is the machine model, and this is the charge device model. It means when you are handling the device or when you are packaging the IC or when you are shipping the IC from one place to another place. On the time also IC can hold some charge, static charge, right. So we have to test that one also. So that is the charge device model. On the time using this crowbar, we will charge the device, then we will connect to the pin to discharge very fast. Actually this is very dangerous because you see when capacitor is discharging, there is no series resistance, right. That means current is very high. So this phenomenon is very critical, this thing, machine model thing. There are some standard application that in some specification they mention some you have to your circuit should pass 8 kilovolt human body model EHD thing. Something they mention. For this one they mention some this amount of current you have to meet EHD thing. Otherwise nobody will buy your circuit. Okay. Okay. So now I will tell some common EHD circuit. So that means, so EHD means huge potential, right? Some spike is coming more than VDD or lesser than ground. Now consider this is your 5 volt signal, this is the 0 volt signal. Some spike has come something like this, very high voltage spike, and duration is very less. And same thing can happen here, right? So you have to discharge that one. So now consider input side. So input side means we consider simple inverter buffer. This is the input side. This is the inside IC, right? This is I portion. So now consider this is the pin. This is the pin region. This is the pin. This is the pin. So we have to put some EHD circuit here. So before going this signal to the internal original circuit, that should pass through the EHD circuit, and EHD circuit will protect the internal circuit, and that will discharge that one, right? This is the EHD circuit. So same thing will be there at the output side. Consider this is output buffer, simple inverter output buffer I am considering. This is the pin. This is the pin. Okay. So some EHD circuit will be here. Okay. Now consider what is there for this one. Very standard one is the diode circuit model. Diode circuit. So this is the pin, right? Pin signal. This signal. We consider this is I, this is O. So this is the I thing. The VDD of the IC. Consider this is 5 volt. Consider this is 5 volt. Okay. So if high spike will come, so when the spike is more than 5 volt, this diode will turn on and will discharge through this path. When spike is lower than ground, then that will discharge through this path, right. So here you can see maximum 0 to 5 within that range, it will not be more than that. This is a very standard diode thing, okay. So if you use the diode thing, so if you use very small area diode, that will not help, okay. So depending on the ESD requirement, you have to decide the diode area, because if you use very small area of the diode, then to discharge that amount of current, diode will burn, right. So depending on the ESD specification, you have to choose how much will be the diode area, okay. Now if you increase the diode area, what will happen? That means your capacitance at that point is increasing. So for high frequency operation, you don't want that high capacitance, right. So that is limiting. So on that time, for high frequency circuit, ESD is very critical, because if you use more area, that will help ESD wise, but frequency of operation will reduce, that is trade off. So high frequency thing, you have to take care about the ESD thing, this is very critical one, okay. These are simple ESD diode thing. So if you want, so people also prefer to use stack of diode, instead of one diode they can use something like this. So depending on the requirement, okay, 2 or 3 they can use something like this. Okay. Now, if to take care the capacitance thing, you are planning to reduce the area of the diode. So that means your DC circuit is weaker, right? Right? So you are making your DC circuit weaker, right? You are reducing the diode area. So for the input side, what we can do? We can add some series resistance here, right? That will help, because when the signal is coming here, the very fast, very sharp rising signal, that voltage spike. So if you see that there is some delay between these 2 points, right? So when before that spike coming here, this circuit will turn on and will discharge that thing. So that this resistance also will help to protect the ESD. So we can use this resistance at the input side. So if you increase more and more resistance, then ESD will be good, but your delay will be more, right? RC delay will be more. So you have to optimize that one also. So you can add this resistance at the input side, because here there is no current is flowing for normal condition. In normal condition, ESD should be off, right? When the normal condition means, you consider this is your 5 volt signaling. So when signal here is 0 to 5 volt, that's a normal situation, right? On the time you see that this diode will not be on, this diode and this diode will not be on. So in normal condition, ESD circuit will be off, but when the spike will come, on the time ESD circuit will turn on and will discharge the charge. Okay. So if you increase the resistance, your delay will be increased. So everything will hamper, performance will hamper, right? Delay performance will hamper.
0 volt comes on the upper part of the diode be on.
No.
What's this?
This is the input side, right? So you can see there is no, in normal condition there is no current flow. So here is some gate, something like this. So there is no current flow, right? So we can't use the resistance at the output side. Now if you consider the output side, so this is the output side. If we add resistance, some resistance here at the output node to protect the ESD, right? To protect the circuit. So what? So when it is charging the capacitance, that means it is driving current. That means you are getting some drop here. So we can't add resistance at the output point. So that resistance we can add at the input side, at the voltage signal level, not the current signal level. If some current is flowing from the external pin, we can't use the resistance, right? So one more thing. So if we use the MOS thing, then the MOS will help. This is a buffer thing, MOS, right? This MOS also will help for the ESD. That is its intrinsic property. How it will help? If I draw the circuit of the MOS, you can get. Okay. Okay. Just I want to show you the cross section of this one. Now consider simple NMOS one. This is the cross section of NMOS, right? Now if you see, this is forming one. Now you consider this is N, and this is P, right? This is forming one bipolar. So this bipolar will help for the ESD phenomena. So if we use the MOS circuit and pin is connected to here or here, right, drain or source region or substrate region, then that will help for the ESD. So that's why if you see the circuit at the input side and on the output side, you can see if the output buffer is very huge, that means that the drain area or source area is very huge. On that time, they are actually people prefer to not to use the ESD circuit, because that MOS, the driver itself will take care of the ESD thing due to this lateral BJT. If you see the characteristic of the lateral, how MOS will help the ESD thing. Okay. Now consider this is the VDS voltage. That means consider this is the VESD voltage. So consider this is simply I am considering this NMOS, and this is connected to pin here. This is the pin, right? And the ESD spike is coming here, ESD voltage. And this is the MOS thing, right? So this is your consider IESD current. If you see the characteristics here, you can see something like this. This is VT1 and this is called VSP, and this is called VT2 and IT2, and this is the permanent breakdown. Permanent breakdown. Okay. Permanent breakdown, this one. So this region. Okay. So when this drain voltage is increasing, current is also increasing. When it is reaching VT1, you can see after that voltage, the avalanche breakdown is happening. So here the junction is there, junction diode. If you remember here, the NMOS, right? So diode will be something like this, junction diode, right? So that junction diode, so avalanche breakdown is happening, and due to that one, this is avalanche breakdown point, and due to that one, you can see some negative differential resistance. This is the negative differential resistance. Okay. So voltage is decreasing, current is increasing. This is called snap black. This is called snap. Snap. This is called some holding voltage. Sorry, this is called some holding voltage, right? So up to this point, current is increasing and voltage is decreasing. So this is a negative resistance region, right? And when it is reaching here, after that, this BJT will turn, the lateral BJT, during this region. The lateral BJT will turn, and it will help to discharge the current there, that charge at the drain node. And if the current here, if the current this IT2, this is the second breakdown point current, if it goes beyond that one, then MOS will be permanently damaged. You can't get back that MOS. So actually this is very critical parameter. If you increase this parameter, then you can tolerate high ESD voltage. So when people will be using output buffer as driver and as ESD circuit, they are characterizing both. They are characterizing MOS characteristics, and also they are characterizing this one, how the ESD phenomenon of the MOS, because it is helping both, right? Okay. Now the layout. Okay. So is it clear up to now? It's clear? Okay. So layout. Now consider some simple MOS structure. So main is the P substrate, right? P type wafer. So this is the P type substrate. Then this is the oxide. Is it visible? Okay. Then this is the poly. These are source and drain. Those are the connection, right? That means this is N plus N minus N most thing. This is source drain, gate drain, right? And this length, this is actually your, this length is actually your drawn length, drawn channel length from here to here. And this is the actual thing, this is the effective thing, because due to the doping, it is some portion is going inside, okay, below the gate. So this is the actual length. L effective, and this is the W of the MOS, width of the MOS. Now, so source, drain, gate are shown, right? Now, how to we have to make the substrate connection, because MOS has 4 terminals. So, to make the substrate connection, we have to use P type, P plus, right? We can't directly add metal here, because if we add metal here, that will act as your Schottky diode, right? Not the ohmic diode, ohmic contact. If you see the characteristic of that one, consider this is your P substrate. You are just directly adding here metal. This is the metal to provide the connection. On the time, if you see the characteristics, okay, you can see something like this. Okay, so but for the ohmic thing, it will be something like this, right? If it is ohmic contact, then it will be something like this is voltage and this is current. But for this one, you will see this one. But if you add here, this is considered P minus, P size, P type substrate. So you have to drop here P plus. Then over that you have to add metal. On that time, you can see these 3 things, and due to the tunneling effect, you can get these characteristics and ohmic characteristics. Okay. So this is the connection for the body. This is for NMOS, this is for PMOS. Okay. Now this is for this is for N and this is for N and P. That is the cross section. Now if you see the actual thing, it looks something like this. Sorry. This is the NMOS, in source drain. This is oxide, this portion I think not visible. The oxide, and this is the gate thing. That's this one. This is the annual thing, and this is your PP, these 2 things. This is gate, this is oxide, the connections. Now, if you consider there actually we have to build MOSFETs, and we have to build the resistances or capacitances on the IC, right? So these are some passive devices as shown here. Now first consider the resistance. Okay. Now first consider there are different type of resistance. Diffusion resistance, then poly resistance. Then are you aware of that one? Diffusion, poly, those things. Poly layer. Okay. That poly gate, poly, right? That layer also we can use as resistance. So first I consider this is called N diffusion resistance, N type diffusion resistance. Okay. So for this one, this is the resistance is 2 terminal. This is the 2 terminal. This is the metal, and this is the actual resistance area. And these 2, this is the N plus and this is the composite. Both will give the actual region, resistance region. This is the actual resistance region. And this is the Salix. This is the salicide process. Salicide process means they are increasing the conductivity of the layers. So if we provide some Salix layer, that means on that area we are reducing the conductivity. So for resistance means we don't want high conductivity, right? So that means we are putting Salix layer. That if we put Salix layer, that means here doping density will be less. Means conductivity of this region will be less. That means we are getting resistance. That's why you can see Salix layer. In the original layout also you can see. I will show that one later. So this is the N type diffusion resistance. The P type diffusion resistance. Okay, this is instead of N plus, this is the P plus. Only difference is that one. This is the actual region. P value you see, this is the N region, N plus, this is the P plus diffusion region. And this is the what? This is the poly resistance. Okay. This is the poly region, this region. Okay, so I am going fast. I think people are sleeping. Okay. This is that is the N plus poly resistance. This is the actual resistance region. This one. This is the poly layer. This is the middle one. This is the contact, and this is the N type, N plus diffusion region. The same thing for here, P plus poly. So why there are different type of resistance? Because for different resistance, you have different seed resistance, right? So you can choose which one you want. Okay, I will tell that one later. why we have different type of resistance, and also different resistance has different temperature coefficient. So depending on the temperature variation, your resistivity will change, right? So poly resistance has one C resistance. You can see this is your P plus poly, 175 ohm per square. Square means 1 square, right? This square. Okay. Have you got it? No. Consider this is the resistance. So I am telling this square. This is W. Sorry, this is L and this is W. So L equal to W for this region. So per unit this square. That is the C resistance here. Okay. So for capacitor also there are different kind of capacitor, poly to poly capacitor, and this is the poly to poly capacitor. Here, this is one poly, this is the second poly, and this is the oxide. Okay, this is called poly to poly capacitor. So this is there in CMOS 9. Which one you are using? CMOS 9 process, and this is very accurate capacitor, but the area is more, comparatively more compared to the other capacitor. This is the capacitor over the substrate, this is capacitor over the NOL. What is the advantage of this capacitor? If we use the NOL below the capacitance, that will reduce to the parasitic capacitance. Consider for this structure. Okay, consider this is one capacitance poly, this is another poly, right? And consider this is the poly 1, this is poly 2, and this is the substrate. Sorry, this is the substrate thing. This is substrate. So you see, this is the oxide. Capacitance between these two is the required capacitance, right? Now you see from here to here this is some oxide is here, right? This is the substrate, oxide is here. So you can see some capacitance here. So this is the parasitic capacitance. If we use the NOL here, on the time what will happen? We are using NOL here, extra NOL, right? You can see some capacitance here to here, and some capacitance here to here. That means both capacitance are coming in series. That means they are reducing the capacitance. Okay.
So won't there be parasitic resistance?
Huh?
Won't there be any parasitic resistance?
Yeah, that will be there. So that is coming from here. You are using some metal connection here, right? You are putting some metal here, then you are routing that one using some metal. So that will give the parasitic resistance. So if you see the actual capacitance, something like this. Capacitance, this is the parasitic resistance, both arm, and both plate you can see some capacitance. This to the substrate, is the substrate thing. This is the accumulation capacitance. So can we remember the function of the MOS? For the NMOS, if you put positive potential at the gate, you can see that electrons are coming towards the channel, towards the interface, right? Oxide and substrate interface, right? And if you use the NOL there, because you have used the NOL here, and this is the your poly thing, and this is oxide thing. If you put positive potential here, what will happen? Electrons will come here, right? That means you are getting one conducting layer here, and that is forming the capacitance. And this capacitance is function of the applied voltage here, because depending on that potential, that accumulation of the electrons here will change, right? And the capacitance value will change. So this is actually very process dependent thing, but the CPP is very accurate one. This is the PMOS thing. If you see from the top level, so in the previous picture you have seen from the side, right? This is from the top. This is the actual width. This is the actual width, and this is the actual length, and this is the poly thing. Poly should be extended beyond the region, right? Otherwise, you can see due to the fabrication process there is some inaccuracy. You can see something like this. Poly has something. Okay. Consider this is your actual width, and if your poly is something like this, there is no extension. What will happen? During fabrication, you can see it can be happen, right? It can be happen. On the time drain and source are sorting. So that means you have to put some extra thing here, this side and this side. So from the top is the view. This is for inmost thing. Oh, this is the guarding I told, right? On that time I told guarding you have to put. So for NMOS, this is the inmost thing, right? So we are putting guarding, because NMOS means substrate is P type, right? We are putting P type substrate here. p type guarding, and we are connecting to ground that one. So we are putting that guarding surrounding that NMOS. So some points we should remember that all modules of the chip should be connected to VDD and ground properly, right? And the VDD line and ground line should be wider, because if you use very thin metal line for the VDD and ground, then when huge amount of current is flowing through that line, you will get huge drop. Consider your supply is on 2 volt. So that 2 volt you are putting in the external pin, but due to that routing thing, if you have very bad routing, what will happen? It will give huge resistance drop. No, sorry, it will give you very huge voltage drop due to that huge resistance, right? Then internally you can see some 1.5 volt. Your circuit will not work. That means VDD and ground line should be wider. And if you have some digital circuit and analog circuit in the same chip, you try to use defined VDD and ground for analog and digital block, because digital VDD means that is very noisy, switching is happening, right? For analog there is less noise, so it is better to use defined VDD and ground for the analog and digital circuit. Okay. So for analog layout, we have to do some matching thing, because matching is very critical. Okay. Okay. Now you consider the can we remember the differential pair, two input transistor? If they are not matched, what will happen? You can get some means proper operation you will not get, right? So if both transistors are not matched, consider a differential pair here. See, both are not matched, right? So actually ideally what will happen? If it is increasing, this is decreasing, the potential here should be ideal, right? There is no change here. But if both are not matched, you can see some spike here, right? So we need the matching between both transistors. When you are simulating the schematic, there will be no problem. But when we are drawing the layout, so depending on the drawing, some portion is coming stronger, some portion is weaker, because you are connecting this portion, this node to this node through some metal, right? If they are not symmetry, what will happen? This has higher resistance, this has smaller resistance. Then that will affect, right? Those things you have to consider for the analog thing. For digital is fine. Okay. So here you can see a mismatch due to two things. One is the random mismatch, another is the systematic mismatch. What is random mismatch? So this is actually this random mismatch will come from the fabrication process. So for this is considered this is a common wafer, full wafer thing. One NMOS is here and another NMOS is here. So at this point, doping density can be different from here, can be different from the here, right? So that will affect, right? So that means here you can see random mismatch due to the doping mismatch, then oxide thickness mismatch, those things. And systematic mismatch, I think if I consider, okay, do you know this one, right? This is the simple n differential per op amp, right? Just I am drawing this one, P thing and P thing. Now if you want to convert to single unit here, what we will do? We will do something like this. Have you seen this circuit? Yes, right? Then it will be coming something like this, going here and you are connecting here, right? You see this is directly connected here and this is going 1, 2, 3 and this is going to 1, 2 to 1 MOS only, right? When if you compare the current here at this point and at this point, you can see this current is more, because due to the body effect here, not body effect, sorry, channel length modulation. Okay, so consider this is 1:1, 1:1, here also 1:1, but due to that channel length modulation, you can see this current is more than this current. Again one channel length modulation is happening here, right? So this current is coming more than 2, instead of coming 1:1 here, it will come something, this current is coming 1.2 times is to 1, something like that. So that will introduce some offset, right? Because this is actually systematic offset, we can avoid that one, right? And some from the bias also. Okay, if you So some circuit you have to provide some bias voltage, and you want to make two circuits symmetry, but the biasing voltage are not perfectly symmetry. Okay, there is some variation. Due to that, you can get some mismatch, right? So that is a systematic option. You can avoid that one. So how does the mismatch of affects the circuits? If you see the current meters here, so due to that mismatch, this kind and this kind will be defined, but you want consider 1:1. That will not be. Okay. So that is happening due to that. So how from where you are getting the mismatch? Mismatch from the VT of this one and VT of this one, and W and L ratio of this one and this one. Okay, these two things. So if you increase this overdrive voltage, you can due to the mismatch, because on the time this effect of this one will be very less, right? Now this whatever I told for the op amp thing. So offset voltage, that is also coming from the mismatch. Okay. Okay. So how to match the transistor? Try to place transistor, the matching transistor. Consider we have to match this one and this one. We have to put this transistor and this transistor very close, right? So that you can see for this wafer, some process variation will be there. So if you go from here to here, some gradient variation will be there. So if you put both transistors very close, the variation will be very less for those two transistors. So that's why place transistor in close proximity, orient transistor in the same direction. That means this is considered M1 transistor and this is M2 transistor. When you are drawing the layout, consider this is your one MOS and this is your another MOS. Okay, that means orientation is different. You see, this orientation is this direction, this is this direction. So that will introduce also mismatch. Okay, so for lower technology is very critical. Consider you are working on 90 nanometer on the time, on 90 nanometer technology. On that time, you have to keep all transistors in the same orientation. Otherwise, that will introduce some mismatch. That means this is not preferred. You draw something like this. If you consider M1 and this is M2, the same orientation, right? Try to keep layout of the transistor as compact. Means you try to put as close as possible. Try to use the common centroid thing. This is a very common thing in the analog layout. If you use the common centroid, that will help to provide better matching. And try to place transistor away from the power supply. Consider this is the MOS, right? If the power supply is running here, here and here, what will happen? It is carrying huge amount of current, right? That means it is generating heat, and due to that one, the performance of the transistor can differ. So try to put transistor away from the power line. But when you are using very low technology, you are planning to reduce the silicon area. On that time also you are planning to you have to put the transistor near the power line. Otherwise there is no option. Otherwise you will need very huge silicon area. That will increase the implementation cost. Okay. So but for lower technology also the current consumption is very less, right? Some milliampere, and also heat generation is very less. So on that time we can use no problem. So it is better to avoid that one. If it is very sensitive to the heat, then it is better to avoid that one. Okay. So resistor matching, the same thing. For when you want to match the two resistance, consider here, instead of two MOS here, you are using resistive load, right? So R1 and R2, you have to match the resistance. Otherwise, you will get different voltage on the same, means on a DC operating condition, right? That is not preferred, because that will introduce some DC differential voltage at the output, right? So you have to match these two resistance, R1 and R2. So matching for the resistance also is required. How to do that one? Now instead of using one resistance is drawing of some poly or something like this, instead of using single strip of poly or metal, you try to finger it, something like this, and you consider this is your R2, and this is R1 and R1, something interdigited thing, right? Now how it will help? Now the process variation is something like this, right? So consider due to process variation, this resistance has reduced minus del x here, and here it reduced minus 2 del x, here minus 3 del x, here minus 4 del x. Now if you average it, you can see the effect is same for the both, right? So you try to interdigit the layout. So capacitance is same, the capacitance is same, and try to place dummy thing. Okay, dummy why is required? Because for these things, because you see here, right? This is the spacing here is uniform, right? Because the spacing is here is uniform. Now if you don't put dummy, means if you don't put here dummy resistance or dummy block here, the dummy same thing. Dummy means you are repeating same block here, but you are not using that one in the actual circuit, right? So what will happen? So environment will be different here. You see it is seeing one piece of poly here, but here is no poly, right? Means full different environment. So the variation for the variation for this one and this one will differ, right? That will also affect the matching. That means you try to use the dummy here, but we are not using in the actual circuit. You can keep it float for the meter, for the resistance, for the capacitance. But for the MOS, you have to properly ground it for the NMOS, and properly you have to put proper supply. Means if you want to use dummy NMOS, you have to connect gate of the NMOS to ground, and for the PMOS, you have to connect this one to VDD, right? Because you have to make transistor off, so you have to put dummy transistor. Okay. Yeah, this is the common center thing. What do I show you? Consider this is the you need consider the two transistors M1 and M2 transistor. You want to match it. Consider M1 is A and M2 is B. So if you do something like this, you can see this will give the better matching. Okay. But how it will help? Because this is considered here. This is your center, right? Right. Now you see with respect to this center, number of drain to the left and right side is same for the B and A. See, for B1, number of drain to the left is here, sorry, to the left is here you see 1, and to the right is 1, and for A also to the left is 1, right is 1, right? How it will help to the matching? Because when the doping is not happening in the perpendicular direction, it is happening something in angle, right? So if it is happening in the angle, then what will happen? So you are putting poly first, then you are doping source and drain region, right? So due to that angle, you can see, what I will say, I have to go there. Here. So if it is happening in this angle, you see this this region will get lesser doping, and this will get more doping, right? So source and drain not symmetry, right? So try to keep same number of source and drain in the left and right of the common center. That will help. Yeah. The different thing. If more number of fingers, you can do something like this. Common centroid layout for the resistance. The common centroid layout, okay, for the MOS. This is B, this is B, this is A, this is A, this is A, this is A, this is B, this is B. Okay. This is for the resistance. So after drawing layout, you have to do some check. Okay. Some design DRC check and LVS check. Design rule check and layout versus schematic check. And after that, you have to do the extraction, and then you have to do the post layout simulation. Because this is the schematic simulation, pre-layout simulation. And if you compare the pre-layout simulation and post-layout simulation, you can get something 20 to 20% variation. Because the parasitic capacitance, resistance, those things will come. You have to consider that one. Why we need the DRC and why we need the LVS here? So DRC means design rule check, right? If you have means you have drawn something, considered here. this is the required thing, actual thing, right? But if you don't run the DRC, and something can happen, means that this region can short here. Okay, so it is not forming the in PMOS. Same thing can happen. So you have to keep some minimum metal spacing here and minimum width. If you don't do the check and if you don't clean it, then means you can get different thing. Means instead of this one, it will be very narrow, something like that, or it can be short. So that is actually the DRC, design rule check. Same thing. You have to keep minimum spacing for the fabrication. Okay. And this is a layout. What is the layout? Layout means layout versus schematic. Whatever you have simulated and whatever you have drawn, both should be same, right? That this check will perfectly match that one, that perfectly check that one. So it will compare the pins, compare the resistance width or metal MOS width, MOS length, everything it will compare. Or also check the connectivity, it's proper or not. Okay. And some models, so square I told, right? The resistivity, see resistance is at 50 ohm per square. This is the 1 square. So if you have resistance something like this, means you can use, this is the 50 ohm, this is 50 ohm, two will come in series. And if this is the fourth thing, you can square it something like this, 50, 50, 50, 50. Okay, so ultimately this is actually 50, right? This is 1 square. This is 50. Okay. So the total resistance will be this length divided by W multiplied by C resistance. That is the resistance of this piece of metal. These are some diffusion resistance. What have I told? Some model will be there, right? Not the perfect thing. This is the resistance thing. This is the required resistance. But this is the parasitic things you see. Okay. This is the your. If you see this structure, this is the actual resistance. This is the diffusion resistance. Implied diffusion resistance. This is the diffusion region. This is one terminal. This is another terminal. This is acting a resistance. But you see from here to here, you will have some diode. This is P and N, right? Some diode will be there. This is a diode. Right. So this is the parasitic diode. And same thing for this is the diffusion thing. And this is a poly thing. One poly. This is a poly resistance. This is one poly, right? And then some resistance will be here. Sorry, some capacitance will be here. I think I have missed the poly one. Poly one is not here. Okay, I have missed that one. Okay. So how to choose the resistance? Which one we have to choose? Because different resistance and different temperature coefficient, different seed resistance, different process variation, and different area also, right? So in some place you need very accurate resistance, and the variation of the resistance over the process will be very less, and but the area will be more. So you have to choose that resistance. In some resistance you need very, you have to implement resistance over the very small area. On the time you have to choose one resistance which has very high seed resistance, but you don't need the accuracy. Okay. So okay, I'm just skipping those things. It's too much. Okay. This is the accumulation resistance. This is the interconnection. Okay. Okay. So if you see this one, this is a simple resistance, but some capacitance will be there, parasitic capacitance, right? This is the actual model. This is this lump model, right? If you use something like this, you have to use this one. Yeah, that's all. Yeah, thank you.